1 million transactions per second is seriously no joke. It is a fact, whether we like it or not, that Bitcoin SV is going to engulf the financial system. The question is, are you going to be the captain on that ship, or are you going to be the waiter on the receiving end? On this channel, we choose to be the captain. We are analyzing the blueprint of Bitcoin, what makes Bitcoin unique, special, right down to the finest details, so that we can equip ourselves with the tools and the knowledge for the new financial future. Welcome to Bitcoin Faculty. In today's video, this is the second part of our series covering hexadecimals and how they apply and are relevant to Bitcoin. Yesterday we covered quite a bit. Today I'll be summing it up, so even if you didn't watch that live, you should be able to understand hexadecimals in the context of Bitcoin. If you don't, I would encourage you to watch that video as we really go into it in a lot of detail. As for today's live, we will be covering converting of hexadecimals to decimals and vice versa. We'll understand why hexadecimal is the preferred method for representing bytes in computing. We will see how or what prefixes are used in Python to denote hexadecimal values. And we will learn about some interesting applications of hexadecimal. So, for example, color references, which I didn't know that they were written in hexadecimal, and even IPv6 addresses. That is a big thing in Bitcoin SV. So we're going to look at that. And then lastly, we'll be concluding by doing a general introduction to base 58. Just to recap what we did yesterday, I am going to share with you my notes. And then let's go through it together. So, we have learned, as of yesterday, of a new number system called hexadecimals. Now, if you've done normal maths, like in school, as in not further than like matric or grade 12, then you'll know about decimals. You'll be quite familiar with normal decimal numbers, okay? It's just normal 1 to 100. Nothing changes. There's no addition of symbols and bits and all those other things, letters. Okay, but now we've learned about hex or hexadecimals, and this is basically what we refer to as base 16 encoding. So what happens is we go in a normal decimal, right, where we would go 0 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. In a hexadecimal, everything stays the same, right, in terms of representing numbers. However, when we get to 10, we now start using letters. So we go A, B, C, D, E, F. And these letters can be uppercase or lowercase. It actually doesn't affect the coding or anything like that. So now, we also learned about binary numbers, which are used in computing, which is basically a 1 and a 0. And that 1 and a 0 is called a bit. And a bit can represent a total of 2 values. two values in terms of number, either a 1 or 0. Then we get into a byte, which is 8 bits. Okay, and we worked out yesterday that by saying, we can remember because it's binary, we always use a 2. 2 to the power of 8 will give us the total number of values that we can get in 8 bits. So when we get a binary here, which is 1, okay, then in decimal it's 1 and 1. When we now go to our next step in binary, which would be a 1 and a 0, what we do to work out, first let's work out what the decimal would be. So the 0, because you'll see we're going to use multiplication, anything that we times by 0, right, it's going to be 0. So we're not going to count the 0, but we're going to say, because normally that would have been 2 to the power of 0, which is 1. But because it's a 0, we're going to ignore it. But there is a 1. So now that 1 becomes 2 to the power of 1. So 2 times 1 is 2. So it becomes 2. So a 10 in binary is 2 in decimal. As for hex, it stays as 2. Because remember down here, 2 in decimal is 2 in hex. All the way basically up until 9. Let's try 11. So we've got 1. So we can say 2 to the power of 0. And anything to the power of 0 is 1. Remember, when we're working with binary, we're working with 2's here. All right. You'll see with hexes, we then work with 16 instead of 2's because it's a base 16 number system. Okay. So we got 2 to the 0, which is 1. And then we've got 2. So this represents 0, 1, 2, 3, and so on, right? So 2 to the power of 1 is 2. And then what we do to convert it to a decimal is we add that up and we get 3. And that's why 11 in binary is 3 in decimal. And 3 in decimal is 3 in hex, as we can see here. Now let's try 100. Remember, we're not going to count the zeros because we're multiplying and it will end up as 0. But where we would start counting, so it starts at 0, then 1, then 2. We're now saying 2 to the power of 2 is 4. So 2 times 2 is 4. It's that simple. So it would be 4 in decimal and 4 in hex. Now I've jumped up a bit in terms of numbers so I can show you an example where this changes, the hex changes to a letter, not a number. So we don't count the 0. This becomes 2 to the power of 1, which is 2. Again, we don't count at 0, but this one will become, this one over here will become 2 to the power of 3. And 2 to the power of 3 is 8. When we add these two up, we get the decimal number 10. 8 plus 2 is 10. But 10 as a hex number becomes A. And that's how we get the answer A as a hexadecimal. So in binary, 1010 or 1010 is 10 in decimal. 10 in decimal is A in hex. Do you see here, and we're going to cover it a bit more in this video, how the benefit, especially if you're working, and remember binary is like the basic computer language. So you can imagine all the combinations of ones and zeros that we can have and how long those numbers can get. Do you see here how we've taken 4 bits and basically put it into a single letter? In decimal, fine, we can do it in two numbers, but in hex, we can reduce that information to 1 letter. And that's actually one of the benefits of using the hexadecimal system. When you see that jumble of letters and numbers in your wallet address or your transaction hash or ID or even the block hash, right? You know that what you're actually looking at is quite simply ones and zeros, but it's being changed to a different number system. It's not always hexadecimal, for example, or maybe the format is, but when it comes to crypto and wallet addresses, there's base 58, which we're going to touch on in this video, and even to an extent base 32. So I'm going to switch over. Okay. So yesterday we did this example. We looked at hexadecimal to decimal, right? And you can check out that video if you want to see how we actually converted this hexadecimal, this combination of numbers and letters, into a decimal, a full-on decimal number. Okay, it's a similar thing. Do you see here we will be using 2 to the power of 0, 2 to the power of 1. You can see we actually do the same thing. We would say, because remember B is 11 on our, call it a number line, B is 11. We would say 11 times 16 to the 0. Anything times 0 is to the power of 0 is 1. So we would end up with 11. And then you do the same here. 3 is 3 in decimal. And then we would say times 16 to the power of 1. So we basically be saying 3 times 16. And we keep doing that all the way across. And then we add up our answers. And you should get to 1072 and 347. We're going to look at converting a decimal to a hexadecimal. So for example, we have our normal number here, 6,735. And what we have to do, remember we're working with a base 16 number. We are going to divide it by 16. And we're going to keep dividing it by 16 until 16 can't go into that number anymore. Now on this note, we're going to do, or I'm going to remind you of the modulo operator that we learned about. The modulo operator in Python makes this task a bit simpler because it's going to calculate the remainder for us. But first, I'll explain how it works to you manually, and then we'll make use of the modulo operator. So the first step is to say 6,735, and we will divide it by 16. We get an answer of 420. Now you may be asking yourself, how do we get to 15 here? That's where the modulo operator comes in. It's this percentage operator. But effectively how it works is you would say, we know it's 420, so we now kind of effectively reverse it. 16 goes into 3,000 6,735. It goes in there 420 times, 420 whole times. So we're going to say 420 times 16. And then all we do is we work out the difference between 6,735 and our answer, which is 6,720. So if you do that on your calculator, you should see that you get 50. We can check it in our operator as well, our modulo operator. So we would say 6735 modulo operator 16. We run it and you see here we get the answer 50. So now the next step is, remember 15 in decimal. How do we convert that to hexadecimal? Well, we know that 15 on our number line of a decimal is F. And so the 15 in decimal becomes F in hexadecimal. But now we're not done. We've still got 420 remaining. So now we are going to say 420 modulo 16, and we get a remainder of 4. So we put our 4. 4 in decimal is the same, it stays the same in hexadecimal. It's 4. If we say 420 divided by 16, we can see that it goes in a whole 26 times. So that's our 26 there. So now we say 26 modulo 16, and we get the answer 10. So we get a remainder of 10. 10 in hexadecimal is A. We can double check it here. If we look for our decimal, there's 10. In hexadecimal, after 9, it's A. So that becomes A. Now we know that 26 divided by 16, it would only go in one whole time. Okay, 26 divided by 16. So it goes in one whole time. So now we're going to say 1 modulo 16, and we get 1. So we are going to put our 1 as the remainder, and 1 is 1 in hexadecimal. And that's our answer because we can't now go any further in terms of getting a whole number when we're dividing by 16. So it explains it again here, but just to finish this question, so 6,735 in decimal is the same as 1A4F in hexadecimal. Right. To convert decimal to hexadecimal, you just need to keep dividing by 60. The remainder of each division gives you the number for each hexadecimal character, from smallest to largest. You then take the result of each division and keep going until you cannot divide the remainder anymore. In other words, until the quotient is 0. Okay, because if you said 1 divided by 16, you're going to get 0, comma, dot, dot, dot. And there it's basically done it for us. Here's the tip, modulus. The modulus operation allows you to find the remainder after division. So we learned all about the modular operator in our very first live stream covering the fundamentals of Python for purposes of Bitcoin and blueprints analysis. So if you are interested in learning and preparing yourself with these skills, then you can go check out that video and kindly like and subscribe. We've got some code examples here. So decimal to hexadecimal, puts 67352, and then there's underscore S, and then 16. So I'm assuming the 16 has something to do with converting it or encoding the number basically to hexadecimal or base 16. Even here, decimal to hexadecimal, there's a reference here to base 16. So in yesterday's video, we also covered a bit of bits and bytes. So just to illustrate here, in a byte, we have 8 bits. I said that at the beginning of this video. If we look here, we've got binary, we've got decimal, and we've got hex. Right. So here in our 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, we can represent them as normal numbers. So remember, we don't calculate the zeros. The 1 would be 2 to the power of, and then we just count the placeholders here. So it's 3, right? That gives us 8. Same thing here. 0, 1, 0, 0. We don't count the zeros. It would be 2 to the power of 2, which is 4. Here, it stays the same. Remember, it keeps going up until 9, and only then do we change to letters. For example, here the 10 becomes an A. It doesn't stay as 10 for hexadecimal. Also take note that hexadecimal, right? They can take 4 bits of information, which is basically half a byte. A byte is 8. Half of 8 is 4. It can take 4 bits and represent it in one value. Okay. You will encounter lots of hexadecimal characters when working with raw data in Bitcoin. For example, here's a random private key. This private key is representing 32 bytes of data. Okay, so if you think about it, 32 bytes. Yeah, I would imagine them, and there's 8 bits in each byte. So you would say 32 times 8, I suppose, 32. So it's got 256 bits of data. Why do we use hexadecimal for showing bytes? Because half of a byte of data has 16 different possible combinations, and there are 16 different hexadecimal characters. Therefore, we can represent half a byte using one single hexadecimal character and a whole byte using 2 hexadecimal characters. So that's what I was explaining to you. This is half a byte, where with the hex, we only need 1 character, and for a whole byte, we only need 2 characters. It says here, half a byte has 16 different possible combinations. Just want to check here. Just give me a second. I want ChatGPT to just explain to me why half a byte of data has 16 different possible combinations. Can you explain why or how? A byte consists of 8 bits. Each bit can be either 0 or 1, which gives you 2 to the power of 8. Okay. Or 256 different combinations in a full byte. So ours, yeah, okay. So I suppose if you want to work out what the different combinations will be, we also did cover this in our video yesterday. Then you would take the number of bits and then you use that as the exponent value. And remember it's 2 because it can be 0 or 1. When you refer to half a byte, you are talking about 4 bits. Each of these 4 bits can also be a 0 or 1. To find the number of different combinations possible with 4 bits, you calculate 2 to the power 4, which is 16. This means that with 4 bits, there are 16 different possible combinations of zeros and ones. Here are those combinations. Great. So the reason I did that is because we are all learning, and if there's anything you feel stuck on, please put it in the comments. There's no such thing as a stupid question. Yeah, I'm in this with you. So we're doing this together. So this is basically taking a binary and converting it to hexadecimal. So I would like to do an example on that based on this. But I'm going to switch screens. So let's take the binary 1, 0, 1, 1, 0, 1, 0, 1. Okay. For example, rather than displaying, I'm just reading here on the website, rather than displaying all 8 individual bits using binary like, we can shorten it to 2 hexadecimal characters. So let's see if we can do that. What we need to do is, first of all, we need to remember that 1 hex digit represents 4 bits. So logically, we're going to break this into 4. We're going to break it into 1, 0, 1, 1 and 0, 1, 0, 1. See? That's my doggy. He's joining me today. So our first one is 2 to the power of 0. Then it's 2 to the power of 1. And then we're going to ignore that 0, which would be 2 to the power of 2. We're going to take the next one, which is 2 to the power of 3. Sorry, 2. Hang on. 0, 1, 2. Yeah, it's 2 to the power of 3. Okay. So 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 3 is 8. So we get an answer of 11. What is 11 as a hex? I'm just going to check the chart. I think it's B. That is correct. It is B. So we're going to write here B. Now let's take the next 4 bits. So this one is 2 to the power of 0, which is 1. We're going to ignore that. This one becomes 2 to the power of 2, which is 4. We add these up and we get 5. Now, 5 in decimal is basically 5 in hexadecimal. So now we've taken a binary number of 8 bits or 1 byte, and we see how we can convert it basically to 2 hexadecimal digits. Basically, the hexadecimal system is a convenient system for displaying raw bytes of data. I'm now going to move on. We've done these examples. So this is a repeat of everything I've said. If you guys are interested in learning and reading more, we are using sailor.org, okay, the Sailor Academy. So you can just go through to his website. The course we're looking at is Bitcoin for developers. And on Unit 5, he provides 2 links for these Wikipedia websites that I'm using. So if you go down to hex encoding 5.3, then the 2 links are in there for specifically for hexadecimal. So again, I don't want to repeat too much. We did this as an example. We've practiced converting binary to hexadecimal. If you want, you can do these examples. We've done hexadecimal to decimal. We did that yesterday. On this website here, there's some, which is the second link, there's some things I wanted to just highlight to you guys. So, in mathematics, a subscript is typically used to specify the base. Remember, we're using base 60. For example, the decimal value 3414 would be expressed in hexadecimal as D56, and then you see there it looks almost like an underscore, says 60. In programming, several notations denote hexadecimal numbers, usually involving a prefix. The prefix 0x is used in C, which would denote this value. So you would say 0x D56. Just to clarify that point, I would like us to be able to recognize when we are dealing with base 16 number systems, whatever the setting may be. So, for example, like we said, mathematics, right? we would say D56, and then over here we would indicate that this is using base 16, which is basically hexadecimal. That's mathematics. But in programming, we would use the prefix 0x, and then it would say D56. And then that immediately tells you, again, that we're using base 16. Then I wanted to also show you, here we go, distinguishing from decimal. In context where the base is not clear, hexadecimal numbers can be ambiguous and confused with numbers expressed in other bases. There are several conventions for expressing values unambiguously. A numerical subscript itself written in decimal can give the base explicitly. So for example, we have 159 and then subscript 10, then that tells you we're using decimal. There where it says 159 subscript 16, it means we're using base 16 or hexadecimal. And that the number 159 is hexadecimal. And then I just wanted to highlight here again what I've said, but just for those of you maybe who are not into Python, that JavaScript, I see a C++, C#, Go, D, Windows PowerShell use the prefix 0x for numeric constants represented in hex. So that's important to know. Syntax that is always hex. We covered this yesterday when we looked at the syntax in transaction IDs, blocks, public keys, private keys. So this is some interesting points, right, about examples where the syntax is in hex. So I mentioned that one of them is actually in color references. So those color numbers that you see, and I didn't know this, magenta, for example, is FF00FF. They're basically hexadecimal digits. I'll just read this for you. It says your color references in HTML, CSS, and Xwindow can be expressed with 6 hexadecimal digits, 2 each for the red, green, and blue components, in that order, prefixed with a hashtag. Okay, and then I didn't realize this till today, any IPv6 address can be written as 8 groups of 4 hexadecimal digits, sometimes called hexadecimal, where each group is separated by a colon. This, for example, is a valid IPv6 address. So it's basically 8 groups of 4 hexadecimal digits. There we go. It can also be abbreviated by removing leading zeros. So there was a 0, but it's been removed. And on that note, we are going to take a short 10-minute break, and then I'm going to show you an interesting article on blockchain and IPv6. Back after that short break. So we were on IPv6. What I find great about this is that initially when we got into hexadecimals, we picked up that it applied to your crypto address, your private keys, your public keys, block hashes, transaction IDs. And now I'm quite excited to discover that part of Bitcoin's SV's vision of scaling is tied to IPv6. So I thought it would be appropriate, now that we know that hexadecimals are applicable, in broadening our knowledge of Bitcoin SV. We now know how IP6 is relevant and what it actually represents. So this is an article on bsvblockchain.org. It says, IPv6 unlocks the true power of the BSV blockchain. The design of the Internet has heralded a new information age of data-intensive applications that have delivered unprecedented communications and convenience to billions of people around the world. As adoption of Internet-based services and applications continues to grow exponentially, the standards which underpin the global network have necessarily evolved to cope with the billions of connected devices and users interacting globally. A prime example of this is the adoption of IPv6, an Internet Layer Protocol standard that allows each device connected to the Internet to be assigned a unique 128-bit IP address. So now we know what a bit is. At the inception of the Internet as we know it today, the IPv4 standard was used to assign addresses to connected devices. IPv4 only allows for 32-bit addresses. However, and as the Internet rapidly grew in the 1990s, it became apparent that far more possible addresses would be needed. Hence, the standardization and adoption of IPv6. The ability to deliver end-to-end networking using IPv6 address space is crucial to unlocking the efficiencies and capabilities of an unbounded blockchain protocol like BSV. The BSV blockchain is the only public blockchain capable of scaling to meet the demands of enterprise-scale applications, and was designed to function as an extension of the Internet that allows for peer-to-peer payments and complex data transfers without intermediaries. And then there's a video on it. I'll put the link of this in the description, and then you can also check out the video. And then just to carry on here, while IPv4 is still widely in use around the world, the address space available using this protocol was fully depleted in 2011, and networking over IPv4 now requires the use of NAT, Network Address Translation, which modifies IP addresses while they are in transit to ensure traffic is delivered to the correct address. To solve this problem, it is crucial that IPv6 becomes widely adopted globally, and end-to-end networking can resume without this unnecessary address translation. The IP4 address space was depleted on the 2nd of February 2011. Since then, we have run out of central address space, but the registries and the ISPs still have some, so they could still use it up to now. But in the meantime, we have deployed IPv6 worldwide. About 45% of the world are using it without knowing it, and that's the purpose of it, Ladid says. So I just wanted to check here. IPv6. So we know that it has 8 groups of 4 hexadecimal digits, and 4 hexadecimal digits represents how many bits? According to my understanding, it represents 4 decimals. So a hexadecimal is equal to 4 bits, right? And the IPv6 has 8 groups of 4. So if we say 4 times 4 is 16, and we times that by 8, we get 128. So going back to this article, that is what they mean when they say it is connected to the internet and it's assigned a unique 128-bit IP address. All right, we've already done binary conversion. We know that it's to the 10, right? Sorry, we use 2. Because this is 2 to the power of 0, right? And 2 to the power of 0 is 1. And the 10 is it superscript? I think it's subscript, indicates that it's a decimal value. And that is base 10. To conclude this learning session, we're going to briefly look at base 58. It is, however, complex, so we won't be able to go into the full nature of it. However, it is relevant when dealing with hexadecimals. And I'll tell you why. If we look at this introduction on the Saylor.org website, Unit 5, Bitcoin data, it says that Bitcoin uses a variety of encoding methods, including some unique methods, checksums, and other techniques. Understanding how Bitcoin stores and transmits data will help you to understand why these methods were chosen. From hexadecimal to base 58, these various techniques help minimize data usage, ensure immutability, and prevent errors. So we can see that we're not only tied down to base 16 as far as Bitcoin is concerned. And it even says here, on completing this unit, we should be able to convert data between hex and base 58. With base 58, as I say, it gets complex. This is actually a course for developers, and we've only just hit the fundamentals of Python, but I'm going to just introduce it anyway. That's not what I was looking for. Let's go to Unit 5. Base Bitcoin addresses and keys. So we're not going to look at converting. We're just going to look at Bitcoin addresses and keys. Actually, never mind. Okay. Bitcoin uses some unique encoding methods, specifically base 58 and base 58 check encoding. This is done largely to prevent errors in transactions. The way that Bitcoin generates addresses and the formats that they are displayed in has been given a lot of thought to prevent confusion and errors. This section covers base 58, key formats, various types of Bitcoin addresses, and more. Base 58 and base 58 check encoding. In order to represent long numbers in a compact way using fewer symbols, many computer systems are mixed alphanumeric representations with a base higher than 10. For example, where the traditional decimal system uses the 10 numerals 0 through 9, the hexadecimal system uses 16, with the letters A through F as the 6 additional symbols. A number represented in hexadecimal format is shorter than the equivalent decimal representation. Even more compact, base 64 representation uses 26 lowercase letters, 26 capital letters, 10 numerals, and 2 more characters, such as, and then you can see which characters they use, to transmit binary data over text-based media such as email. Base 64 is most commonly used to add binary attachments to email. Base 58 is a text-based binary encoding format, developed for use in Bitcoin and used in many other cryptocurrencies. It offers a balance between compact representation, readability, and error detection and prevention. Base 58 is a subset of base 64, using upper and lowercase letters and numbers, but omitting some characters that are frequently mistaken for one another and can appear identical when displayed in certain fonts. Specifically, base 58 is base 64 without the 0, as in the number 0, a capital O, a lower L, and a capital I, as well as the symbols, and then it's also got the symbols here. So one can appreciate that 0 could be confused with O, or capital O could be confused with 0, and even an L, or in the case of a capital I, it could be confused with 1. So they've intentionally omitted those for the purpose of Bitcoin. More simply, base 58 is a set of lowercase and capital letters and numbers without the 4, being 0, capital O, and a lowercase l or an uppercase I, just mentioned. Bitcoin's base 58 alphabet shows the full base 58 alphabet. And then we've got it here. So we go up to 9, we go up to F, right? So 9 would be the decimal number system. When we went up to F, it was the hexadecimal number system. Now, what they've done is they've added all the alphabets. So there's uppercase and then there's some lowercase. And that is now what base 58 looks like. So we only used to, at this point, we used to seeing it up until this point, up until F. Now let's learn a little bit about base 58's check. To add extra security against typos or transcription errors, base 58 check is a base 58 encoding format frequently used in Bitcoin, which has built-in error checking code. The checksum is an additional 4 bytes added to the end of the data that is being encoded. The checksum is derived from the hash of the encoded data and can therefore be used to detect and prevent transcription and typing errors. When presented with base 58 check code, the decoding software will calculate the checksum of the data and compare it to the checksum included in the code. If the two do not match, an error has been introduced and the base 58 check data is invalid. This prevents a mistyped Bitcoin address being accepted by the wallet software as a valid destination, an error that would otherwise result in loss of funds. To convert data, a number, into a base 58 check format, we first add a prefix to the data called the version byte, which serves to easily identify the type of data that is encoded. For example, in the case of a Bitcoin address, the prefix is 0, so that in hex format, that would be 0x00, whereas the prefix used when encoding a private key is 128. So that would be 0x and then 80 in hex. A list of common version prefixes is shown in base 58 check version prefix and encoded result examples. So now we're getting into a lot of detailed coding and how the payload works. Yeah, for me, this is just, it's taking it a bit too far for us at this stage. So I'm quite happy with where we are now. We have learned about hexadecimals. We've learned about how it applies to Bitcoin, why it's used in Bitcoin. We have learned about the benefits of using hexadecimals when we're dealing with binary numbers. We've learned how to do the conversions. We've learned some other interesting use cases, for example, IPv6, and how hexadecimals are being used to advance scalability on the internet, which is the whole narrative of Bitcoin SV. And we've also learned a little bit about when we're dealing with hexadecimals, there is also a relationship with base 58. We at least have an understanding at this stage when it comes to base 58. We know what it would look like from a base 16 perspective, and that we at that point just adding further letters and numbers. We should have an understanding of what base 16 actually means as a number system, and even base 10. And yeah, I am otherwise quite happy. We're going to end the video for today, and from tomorrow we'll be carrying on with our basic operators in Python. This was indeed very interesting, and I'm happy we have found some relevance in relation to Bitcoin, because at the end of the day, we're not doing Python just for the sake of it. Like I always say, we're doing it for a purpose, which is to equip ourselves for the technology that is Bitcoin SV. And I hope so far you found it useful and you're understanding. And yeah, if you're interested, keep looking into like Sailor.org and even learnpython.org. They have certificates which you can get, which is great to add to your LinkedIn. And yeah, just like I said, expand your skills. Thank you so much for watching, and I'll catch you guys tomorrow, same time.